Hello all, welcome to the basics.academy. This is Smart Contract Security, Fundamentals and Auditing, a 5 units, 3 credit course in the BSc Blockchain Technology program. Let's get into it. Today we are going to look into access control and events. First, we will check the ownable pattern. Then we will discover the role-based access patterns. After that, we will focus on events and what are index parameters in events and what is the importance of indexing a parameter and how does that help for filtering on the front end. And then at last, we are going to make use of events for off-chain indexing. In today's roadmap, we will try to close the gap left by visibility specifiers alone. By doing so, we will come to know the importance of why we need access control and not some ad hoc checks. Secondly, we are going to explore the ownable pattern, the single address privilege, transfer of ownership, and the limits of ownable pattern. Thirdly, we are going to look into role-based access control, which involves granting distinct permissions to distinct roles instead of one owner. And at last, we are going to have a look at events and index parameters and how off-chain applications track on-chain state changes efficiently. This is going to be our shortest topic in Unit 2, so expect more depth per topic and a closing tie back to everything we have covered across lectures 1 and 2. Why access control needs a standard pattern? The visibility specifiers such as public or external or internal or private, they control who can call a function. However, they say nothing about who should be allowed to. For example, this set fee percentage, its visibility specifier is external. It can be called by anyone. Whoever calls this function will set the state variable fee percentage is equal to the new fee which is being passed as a function argument to this function. However, by far we haven't answered why access control needs a standard pattern. The answer is as follows. A missing or misapplied permission check. This is one of the most common categories of finding a bug in smart contract audit. Secondly, ad hoc checks scale badly. For example, if you use require msg.sender equal to owner throughout the contract, this is as good as you are repeating the code, which is violating the try principle. Whereas, if we standardize this pattern, that is, if we standardize the access control pattern, what we can do, a modifier is defined once and it can be used on different functions across the smart contract. Here, we are not even copy pasting the code, and if at all something breaks, all we have to do is fix the code just at one point or just at one loop. The ownable pattern. What is the ownable pattern? We have a contract, ownable, and inside this contract, we have a modifier onlyOwner, which checks that the caller is equal to the owner. Now, what is this owner state variable value? This owner state variable value is set whenever we deploy a contract that is inheriting from the ownable smart contract. So, if at all you need some functionalities that can be called only from the owner contract, all you have to do is just add this modifier to that function invocation. For example, here we have transfer ownership. Now this transfer ownership function, its visibility specifier is external. However, it can only be called by the only owner, that is the wallet address which is the owner of the smart contract. If at all you are trying to call transfer ownership from any other wallet address, this required check will fail. That will lead to non-execution of this transfer ownership function. One thing to notice, inside modifier, first we add the checks and then at last we add an underscore. What is the role of underscore? At runtime, what Solidity does, this underscore is replaced by the function body of the calling function. At runtime, this underscore is replaced by the body of the calling function. In this case, when transfer ownership implements the modifier onlyOwner, after this check, this underscore is replaced by this code. That is the importance of underscore inside a modifier. So this is all about ownable pattern, in which we have declared a modifier only owner, and whichever contract inherits from ownable can make use of the only owner modifier in order to ensure that those functions are being invoked by only the owner of the contract. How can we apply only owner in practice? Prior, we have seen a set fee percentage whose visibility specifier was external, and that can be called by anyone. So right now what we have done is we have created a FeeManager contract which inherits from Ownable. This contract has a set fee percentage which takes a new fee value. Its specifier or visibility specifier is external, and it can be called only by the owner of the contract. First we check the new fee should be less than or equal to 10,000. If not, we return an error, fee is too high, else we set the fee percentage to the new fee value. However, prior to execution of these two lines of code, first the only owner modifier is kicked in. That is, this modifier is kicked in, which checks the caller is the owner. If not, it will return an error and the transaction will be reverted. If yes, the check passes, and this underscore is then replaced by the set fee percentage function body. So what happens? Here we are using one keyword which gives us consistent protection. That is, only owner reads clearly at every call site and is checked identically everywhere it appears. Single point of failure by design. If the owner's private key is compromised, every only owner function is compromised at once. This is the main limit or drawback of the ownable pattern. Now, this limitation motivates the next pattern. What happens when different functions need different trusted parties? A single owner is the wrong shape, right? We discussed about the ownable pattern, the only owner modifier, then the single point of failure, that is, if the owner's private key gets compromised, every function that is governed by only owner modifier gets compromised. This limitation motivates us for the next pattern, which is our role-based access control pattern. Role-based access control, or RBAC. Instead of one owner, RBAC grants distinct permissions or roles to distinct addresses. A role can be held by multiple accounts, and one account can hold multiple roles. That is, if there is an account address 0x1234, that address can be a minter, that address can also be a pauser, and that address can also be a default admin. What is a minter role? The minter role allows to mint new tokens. If there is a mint function, and on that mint function, if you have added the modifier minter role, that mint function can only be called from the wallet which has the minter role. What is a pauser rule? In case of a hack, if something goes wrong and your contract has implemented the pausable functionality, in that case, there are certain wallets which are given the privilege to go ahead and pause the transaction, thereby mitigating the hack or mitigating the risk or mitigating the loss. What is the default admin role? The default admin role, this wallet is responsible for granting all different kinds of roles, be it minter role, pauser role, or any other custom role. The simplest way to implement role-based access control is by making use of OpenZeppelin's access control contract. By making use of OpenZeppelin's access control contract. This is our token contract, which is inheriting from access control. And at the top level, we have defined two state variables. First is the minter role, and second is the pauser role. How the minter role and pauser role are calculated? It's by making use of the ketchak256 hash function and passing in the constant string minter role in case of minter and pauser role in case of pauser. So this returns a 32 bytes hash. Now inside constructor, we are calling the grant role function. This grant role function is defined inside the access control smart contract. First, we give the default admin role to the message.sender or the caller who is deploying this contract. And secondly, we are also giving the minter role to the caller or deployer of the smart contract. Then look at the mint function. This mint function is governed by the minter role, or this mint function can only be invoked by a wallet address that has minter role. Then secondly, we have a pause function. Now this pause function can only be called by a wallet address that has a pauser role. Have a close look at only rule. This modifier is also defined inside OpenZeppelin's access control smart contract. So the easiest and the simplest way to make use of access control inside Solidity is to inherit your contract from OpenZeppelin's access control smart contract. Let us now look into the ownable pattern versus the role-based access control pattern and decide when to choose one. When the number of trusted parties is only one, it is recommended to go with the ownable pattern. Whereas, if the number of trusted parties can be any number, in that case, you are recommended to go with the role-based access control pattern. If you need fine-grained control over your smart contract, that time go with RBAC. Whereas, if you need all or nothing kind of pattern, go with Ownable. How can we decide the best fit either for Ownable or RBAC? In case of Ownable, simple contracts, single deployer or admin. Whereas in case of RBAC, if there are multi-team or multi-function systems such as mint, pause, upgrade, etc., and all these things are separated, during that you are supposed to go with RBAC and not with onlyOwner or ownable pattern. What are the complexity cost of Ownable? Ownable's complexity cost is minimal and it is the easiest one to audit. Whereas in case of RBAC, the complexity is higher, more surface area, because the role management itself must be secured. One tip going forward is to use the simplest pattern that fits. Adding RBAC to a contract that only ever needs one trusted address just adds unaudited attack surface for no benefit. If at all you only need one address, in that case, don't go for RBAC. That will just add unaudited attack surface. Never ever do that. If you need multiple roles, then go with RBAC. If only a single address suffice your use case, go with the ownable pattern. Access control pitfalls to watch for. First is a function that should be restricted but has no modifier at all. For example, imagine there is a transfer ownership function without the onlyOwner modifier. Authorization checked with tx.origin instead of message.sender. Never ever use tx.origin, always use message.sender. Initialization functions left callable after deployment. This is applicable in case of upgradable smart contracts. After upgrading the smart contracts, there is a initialize function which you are supposed to call. If that initialize function is not guarded by the initializable modifier, that would lead to state corruption inside the upgraded smart contracts. Role or ownership renounced or transferred without a recovery plan. This is the most important. If you call renounce ownership, what happens? The owner is set to an address 0. When the owner is set to an address 0, all the functions governed by the onlyOwner modifier becomes non-callable. The fix here is to use Ownable two-step. When you use Ownable two-step, in that case, as soon as you begin the transfer ownership, the new owner is being notified, and when the new owner calls accept ownership, only then the ownership transfer is completed. How Ownable two-step mitigates the risk of transferring ownership to an invalid account. Let us say you invoked transfer ownership with address 0 using Ownable two-step. You have completed the first step. For the second step, the new wallet address must call accept ownership. Since the new wallet is address 0 that does not have a private key, hence it cannot call accept ownership, thereby protecting you against transferring the ownership to the wrong address. It's my personal recommendation, always use Ownable two-step instead of Ownable. Events, why they exist. Events write to the transaction log and not to the contract storage. Hence, they are far cheaper to write than a store, but they are not readable from within the EVM by other contracts. The purpose of events is to enable off-chain visibility. When we say off-chain visibility, it includes dApp frontends, indexers, and monitoring tools that subscribe to logs to know when contract state was actually changed. Imagine events to be the standard way of signaling something has happened on the blockchain. That can be a mint, a transfer, an ownership change, a role grant, anything an off-chain system needs to react to. How events are defined inside the smart contract? Using the keyword event, followed by the name of the event, then the argument which your dApp needs or which is needed for off-chain visibility. This is how you define an event. This is how you emit an event from within the smart contract. Event syntax and emit. Events are declared like a function signature but without any body. With event, you can add up to 4 total parameters. That is, inside events, you can add up to 4 total parameters. And emit is required to actually write the log. This is our transfer function. First, we update the state, and at the end, we emit an event. When we emit an event, this is written to the transaction log. What is the indexed keyword in event used for? Here we have transfer event, and inside transfer, before, from, and to, we have added the keyword indexed. What is the purpose of indexing event parameters? The simplest redefinition, the parameters which are indexed helps us to create a filter on the off-chain side to query the transaction logs or the event data more efficiently. Is there a limit on the number of index parameters inside an event? Yes, you can define at most 3 parameters that can be indexed. Now these indexed parameters become searchable topics. That is, you can create a filter on the off-chain side for the index parameters and you can get all the details in one go. Off-chain tools can filter directly on indexed values. Non-indexed parameters are cheaper to store, but they are not filterable this way. So the mental model is, whenever an event has indexed parameters, those parameters can be used to create filters on the off-chain side to query data more efficiently. Why indexing matters for off-chain monitoring? First is dApp frontends. If you want to track live incoming transactions or tokens into the connected wallet, you can listen for events. Second, security monitors. If at all an ownership transferred event emits, which indicates ownership transfer has started, the security team can flag it based on the address of the new owner, whether it is controlled by the team or not. And at last, indexers and analytics. Protocols like the graph build queryable databases by replaying the indexed event history rather than rescanning the full chain state. So this is why indexing matters for off-chain monitoring. Let's recap access control and events. First, visibility controls who can call a function. It says nothing about who should. When to use Ownable, when you need one trusted address. When to use RBAC or role-based access control, there are many addresses, each scoped to specific permissions. Third, never authorize with tx.origin. Even inside a modifier that looks secure, always make use of msg.sender and never use tx.origin for authorization. At last, events are cheap, off-chain only signals, index the parameters your off-chain consumers will actually filter on. Visibility controls who can call a function. Ownable when you need a single party. RBAC when you need multiple parties. Never authorize with tx.origin. Make use of events and index parameters for off-chain filtering and indexing. So this wraps up our Unit 2. In Unit 2's first lecture, we covered types, visibility, then message.sender versus tx.origin. Then at last we looked at payable, fallback and receive. In lecture 2, we talked about error handling wherein we discussed in detail require, assert, revert, then switched to custom errors, looked into gas fundamentals and at last completed storage packing. And in today's lecture, we discussed ownable pattern, role-based access control, what are events and what is the importance of index parameters. So up next for the practical, all we have to do is first deploy the contracts using Remix on Sepolia testnet, then write and run the hard hat tests that exercise everything above. The ownable pattern and the role-based access control pattern. First, we are going to deploy those using Remix. Later on, we are going to write unit test cases for those contracts using the hard hat framework. So this wraps up Unit 2. That wraps up this session. If it helped, like and subscribe so you don't miss the next one. Questions? Drop them in the comments below. See you in the next lecture.